We have reached the last section of the course. I want to congratulate you for your determination to get to this point, and I'm sure you're going to have a lot of success ahead of you. In this section, we're going to continue our discussion of graphs and their algorithms. We'll be focusing on undirected and weighted graphs. So let's jump in and get started. Earlier, we talked about weighted graphs. If the edges of our graph have weights, we say we have a weighted graph. These weights can represent factors such as cost, distance, complexity, literally anything. A common application of weighted graphs is in finding the shortest path between two nodes. Let's say these nodes represent different areas in a city, and the weights on these edges represent the distance or traffic conditions between these areas. Soon, I will show you an algorithm to find the shortest path between two nodes. But before we get there, I want you to implement a weighted graph. So create a new class called weighted graph. In this class, we should have a private node class just like before, but we should also have an edge class. This class represents the edge between two nodes. So we should have three fields. From and to, these are both node objects, and weight, which is going to be an integer. For now, only implement two operations in the weighted graph class, add node and add edge. Just remember, this method should have three parameters, from, to, and weight. Also, I want you to make this graph an undirected graph. In an undirected graph, our edges don't have a direction. So if you add an edge between A and B with a given weight, we should also have an edge from B to A with the same weight. So spend 10 to 15 minutes on this and then come back here. All right, let's add a new class. We call it weighted graph. Now, to save time, I'm going to borrow some code from our existing graph implementation. So over here, first, I'm going to copy the code for the node class. So copy and paste it over here. So far, so good. Now we need to implement the edge class. So private class edge. Here we need three fields. From and to, these are both node objects. So private node from and to. We also need the weight. So private integer weight. Now I'm going to create a constructor to easily initialize an edge object. So let's generate that real quick. I'm going through this super fast because you have seen several examples of me doing this throughout this course. If you think I'm going too fast, then you probably have to go back and start from the beginning. So here we have a constructor. It's also good to override the toString method, especially if we're going to debug this program. We can easily see the output of an edge object in the debugger. So let's generate a toString method. Now I'm going to simplify this expression and only return from plus this arrow and to. With this, we're going to get something like this. A goes to B. Pretty useful. So we're done with the edge class. Now, back to our graph implementation. Here we have two hash tables, one to store the nodes, one to store the adjacency list. In this implementation, we're mapping a node to a list of nodes. But in our new implementation, we should map a node to a list of edges because each node can have multiple edges. So back to the weighted graph. Let's add these hash tables real quick. So private map of string and node. Let's import the map. We call this nodes and set it to a new hash map. Next, we're going to create a map of node to a list of edge. We're going to call this adjacency list, just like before, and set it to a new hash map. We're almost done. Now, finally, we need to implement two operations, add node and add edge. So I'm going to bring these two methods, as well as the print method for verifying our graph, into our new implementation. Now, we have a few compilation errors, but they're really easy to fix. So as we pasted this code, IntelliJ thought we are referencing the node class inside the graph class. But as you know, this class is private. We cannot access it. But here we don't care about the node class inside the graph class. We want to work with the node class we have defined here. So let's remove this prefix. The error is gone. So this is how we add a node just like before. Now let's work on the add edge method. Here we need to add a third parameter, that is the weight. Now, just like before, we validate the from and to arguments. If they are valid, we go to our adjacency list. We get the entry for the from node, which is a list of edges, and then we should add a new edge to it. That is why we have a compilation error, because we're trying to add a node object to a list of edges. So here we need to add a new edge object. As the first argument, we should pass the from node, then the to node, and finally the weight. Now let me put this on a new line so you can see all the code in one place. So this is how we add an edge. Now earlier I told you to implement this class as an undirected graph. So when we add an edge from A to B, we should also add an edge from B to A. That is super easy. So we go to our adjacency list, get the entry for the to node. This will return a list of edges. Then we'll add a new edge. So a new edge, our arguments are to node, from node, and weight. Okay. Now we have a weighted undirected graph. Let's test our implementation. So I'm going to go to the main class and create a new graph, a new weighted graph. We give it 3 nodes. Let's say A, followed by B and C. We also add an edge from A to B with the weight of 3, and one from A to C with the weight of 2. Finally, we call graph.print and run our program. So, as you can see, A is connected to B and C. Now, because we have an undirected graph, here we have 2 inverse relationships. So B to A is the inverse of A to B, and C to A is the inverse of A to C. This is a weighted undirected graph. So this is our current implementation of weighted graph, but I'm not quite happy with this implementation. Why? Well, the concept of a node and an edge are tightly related. So it would be better if our node class had a list of edges, just like the node class that we implemented earlier for a binary tree. Each node of a binary tree has a reference to its left and right children. So once we have a reference to a node, we can navigate the tree. This is a more object-oriented approach. But here, first we have to look up a node using a string in our first hash table. Then we have to go to our second hash table to find the edges of that node. There is a disconnect here. So I'm going to get rid of this adjacency list and have each node store its edges. Conceptually, we're still having an adjacency list because we're storing only the edges that exist, not the combination of all edges. So we don't have an adjacency matrix. But this is going to be an object-oriented implementation, which is different from what data structure textbooks teach you. So let's get rid of this hash table over here. We immediately have a few breaking changes. Don't worry about them. We're going to fix them real quick. So in the node class, we're going to introduce a new field, private list of edge. We call it edges. And here we set this to a new instance of array list. Now we could also optimize this. So instead of having a list of edges, we could have a map of edges. This way we can quickly check to see if a node is connected to another node. We don't have to iterate this entire list, but let's leave it for the future. So each node has a list of edges. Now I would like to add a public method here, public void add edge. So we want to connect this node with another node. What parameters do we need here? The target node and the weight. Okay. Now in this method, we're going to create a new edge object and add it to this list. So we call edges.add, and here we pass a new edge object. Here we need to pass 3 arguments. The first one is the from node. That is the current object over here. So we pass this, which is a reference to the current object. The second argument is going to be the target node, and finally the weight. So we use this public method to add an edge to a node. We don't care how a node maintains its edges. Currently, it's using a list. In the future, we might replace the list with a hash table. As long as we rely on this public method and don't go in the implementation, we're going to be fine. So we're not going to have breaking changes, okay? Now, let's fix the breaking changes. In the add node method, because we don't have the adjacency list anymore, we have a compilation error. But we can safely delete this line because now when we create a new node object, that node automatically initializes its edges to a new array list. Let me show you. So when we create a new node object, the edges field automatically gets initialized to a new instance of the array list. So we don't have to do this manually. So this is going to make our implementation shorter and cleaner. We could also get rid of this local variable because it's only used in a single place. So we can pass a new node object with this label over here. That is better. Now let's look at the add edge method. Here we have a compilation error when adding an edge, but that is super easy to fix. All we have to do is to call the add edge method. So we call from node that add edge. We pass the target node and the weight. Similarly, we call toNode that add edge. We give it the from node and the weight. Look, our new implementation is shorter, cleaner, and more expressive. It's easier to understand than this previous implementation, right? So delete and delete. Now finally, we need to fix the print method. So here we need to get the list of nodes. Currently we're getting them from our adjacency list, but we can easily get them from our nodes hash table. So nodes.values. This method will return all the values in our hash table. These values are node objects. So let's also rename this to node. That is better. So for each node in this graph, we want to get the neighbors of that node. We can go directly to node.edges, but this is not something that I recommend because this edges field is implementation detail. Tomorrow, we might replace this with a hash table. If we do that, this code is going to get broken. So to prevent that, we're going to go back to our node class and introduce a new public method. So public, we return a list of edges, call it get edges, and currently we return just the value of the edges field. Now in the future, if we change the type of this field to a hash table, then we can convert that hash table to a list by calling the values method. So the clients of our class are not going to get affected. This is the only place that we'll have to modify, okay? So let's return the edges field. Now back to the print method. Here we call node.getEdges. So let's rename this variable to edges. That is better. I believe we are done, but let's test our program. So let's quickly run it. There you go. We get the same result as before, but now we have a cleaner and more object-oriented solution. Dijkstra's shortest path algorithm is one of the classic algorithms for finding the shortest path between two nodes of a graph. It was developed by a Dutch computer scientist called Dijkstra. So here we have a simple weighted graph, and we want to find the shortest path between A and E. With this algorithm, we're going to generate a table of information like this. In this table, we can see the shortest distance from A to every other node. Initially, we assume the distance from A to A is 0, and the distances from A to all other nodes are unknown. So we set them to a large value. As we navigate in this graph, if we find a shorter path, we'll update this table. Let me show you. So we start from A. At each step, we look at the unvisited neighbors of the current node. So the unvisited neighbors of A are B, C, and D. Now we calculate the distance from the start node to each of these neighbors. In this case, the start node and the current node happen to be the same node. That's the A. So what is the distance from A to B? It's 3. We compare this with the known distance to B. That is what we have in this table. Since we have found a shorter distance, we should update our table. So we set the distance to B to 3. Now, how did we get to B? Via A. So we need to record A as the previous node in our table. We'll need this later when we construct the full path between two nodes. Basically, every time we find a shorter path, we need to record where we came from. That is the idea. So let's repeat this step for other neighbors of A. The distance to C is 4, is shorter than what we have recorded in our table, so we should update our table. And one more time for D. We're done visiting the A. Now we look at the neighbors of A and pick the one with the shortest known distance. Out of these three, D is the closest, so we're going to visit it next. Now we repeat these steps. We look at the unvisited neighbors of the current node and calculate the shortest distance from the start node to each of them. If we find a shorter path, we'll update our table. So D is connected to every other node in this table, but out of these, we have already visited A, so we ignore that. Now we calculate the distance from the starting node to each of these neighbors via the current node. We know the distance from A to D. We also know the weight of the edge from D to B. So the distance from A to B via D is 2 plus 6. Now we compare this new distance with the shortest known distance to B. Our new distance is not less than 3, so we're not going to update our table. The shortest distance to B is still what we have recorded in our table, okay? Now let's calculate the distance from A to C. That is the distance from A to D, which is 2, plus the distance from D to C. Now we compare this with the shortest known distance to C. Obviously, we found a shorter path to C via D, so we should update our table. One more time. Let's calculate the distance from A to E via D. It's 2 plus 5. Obviously, it's shorter than the known distance, so we update our table accordingly. We have visited all the neighbors of D. Now we should pick the closest one and go there. Out of these, we can go to either B or C. Let's go to B. We repeat our steps. We look at the unvisited neighbors of B. That is E. We calculate the distance from A to E via B. That is 3 plus 1. This is shorter than the known distance to E, so we found a shorter path and we should update our table. The shortest distance to E is now 4 via B. We're done with B. Now we need to find its closest unvisited neighbor. That's E. At this point, we have visited all the neighbors of E, so we're done here. The only node that is left is C. But again, we have visited all the neighbors of C, so our algorithm stops here. Now in this table, we can see the shortest distance from A to each node in this table. And using the previous node column, we can build these shortest paths. For example, let's say we want to print the shortest path from A to E. We know we got to E via B, and we got to B via A. So the shortest path from A to E is A, B, E. So this is Dijkstra's algorithm. This algorithm is an example of what we call a greedy algorithm. A greedy algorithm tries to find the optimal solution to a problem by making optimal choices at each step. In this case, at each step, we try to find the shortest path between the current node and its direct neighbors. That's a greedy algorithm. To implement this algorithm, we need to perform a breadth-first traversal in our graph. So we're going to use a queue to implement this, just like how we implemented the breadth-first search algorithm. However, the order of nodes we visit is a bit different in this algorithm. In the breadth-first search, the order didn't matter. But now as we're done visiting a node, we want to go to its neighbor that is the closest to the start node, okay? So here we need to use a priority queue instead of a regular queue. We talked about priority queues in the first part of this course. In a priority queue, items move to the front of the queue based on the priority. So as we're examining each neighbor, if we find a shorter path to a neighbor, we update our distances table and push a new item into our priority queue. So the priority of this item is going to be equal to the new distance we have calculated. So if a neighbor is closer to the starting node, it will be moved to the beginning of the queue, okay? Now for this exercise, I want you to use the priority queue class in Java. Let me show you how it works. First, I'm going to declare this method, public integer get shortest distance. We give it 2 parameters, from and to. Now here we want to create a priority queue object. The class that we are going to use is the one that is declared in the java.util package. As you can see from these angle brackets, this is a generic class. So here we need to specify the type of objects that we want to store in this queue. So here we want to store node objects. Let's create this queue, new priority queue. Now look at the constructor of this queue. This constructor is overloaded, which means we have a few different ways to call it. One way is to pass the initial capacity. Another way is to pass a comparator object. What is this comparator? Well, this is an advanced topic, and I'm going to cover it in my upcoming advanced Java course. But for now, let me give you a quick fix. This queue uses a comparator to compare two objects. The job of this comparator is to determine which object should be moved to the beginning of the queue. So here we need to create a comparator object and pass it to our priority queue. But how are we going to do that? Well, here we have this comparator interface. So let me put this on a new line. Comparator. Look, this interface is declared in the java.util package, and it has a method called comparing int. This is a factory method that creates a comparator object for comparing two integers. Now, what is that integer here? That is the priority of a neighboring node. Let me show you how to use this method. So we call this method, and here we need to pass a function. Now I'm going to show you a shorthand to create a function. If it looks strange to you, don't worry about it. Just bear with me. I will cover this in detail in my upcoming advanced Java course. So this function is going to take a node object because every object in this queue is a node. So I type n here. This is like the parameter of that function. Then we add this arrow. And after this arrow, we write the body of that function. We want that function to get a node and return the priority of that node. So we can type n dot, but here we don't have a priority field. We only have edges and label. One way is to add the priority field here, but this is a bad approach because we need this field only for this algorithm, nowhere else. So we don't want to pollute this class with fields for different algorithms. That is a bad practice. A better approach is to wrap this class inside another class and call it node entry. Let me show you. So temporarily, I'm going to comment out this code. And let's just return 0 to fix this compilation error. In this class, we're going to declare a private class, node entry. This class is going to have two fields. One is a node. The other is the priority of that node. So integer priority. And just like before, let's create a constructor to initialize these two fields. Okay. Now, back to our priority queue. Let me bring this code back in. Now that we have this new class, we want to create a priority queue of node entry. So every entry in this queue is a node entry object, right? Now, when we call comparator.comparingInt, instead of a node, we're going to have a node entry. So I use NE as an abbreviation of node entry. We could call this anything. We could call it X. It doesn't matter. It's like the parameter of a method, okay? So node entry goes to node entry dot priority. So this small anonymous function that we're creating here takes a node entry object and returns the priority of that object. Now, this comparing int method will create a comparator object based on this function. So as we add node entry objects to our queue, this comparator object is going to look at the priority of these node objects and determine what node object should be moved to the front. Okay? So when we create a new priority queue object in the constructor, we should pass this line. So this is all about this priority queue. Now, in this algorithm, we need to create this table. How are we going to do that? That's super easy. Basically, we need two hash tables. In both these hash tables, our keys are node objects. Our values are different. In the first hash table, our values are integers. We can call this hash table distances. In the second hash table, our values are node objects. So we map a node to another node, to its previous node, okay? So go ahead and spend 20 to 30 minutes on this exercise and then come back here. In this video, we want to calculate the shortest distance between two nodes, and we'll look at finding the shortest path in the next video. So first, we should create our distances hash table. We want to set the distance to all nodes except the starting node to the maximum integer. So we create a map of node to integer, call it distances, and set it to a new hash map. Now for every node in this graph, we need to add an entry in this hash table. So for var node in nodes.values, in each iteration, we call distances.put, we pass the node and integer.maxValue as the arguments. Now we should set the distance of the starting node to itself to 0. So after our for loop, we call distances.replace. Here we need a reference to the starting node. So we call nodes.get and pass from. This will return our node object, and then we'll pass 0 as the value. We're done with this. Next, we should create a set for keeping track of the visited nodes. So a set of node, we call it visited, and set it to a new hash set. Now to kick things off, we should add our starting node to our queue. So queue.add. Look, here we should pass a node entry object because every object in this queue is a node entry object, okay? So let's pass a new node entry. Now here we need a node object. That is our starting node. We already got that object from our nodes hash table. So let's reuse this. I'm going to extract this into a variable called from node. And then we can reuse this in both these places. Now, as a second argument to the constructor of node entry, we should pass the priority. What is the priority of the starting node? We can pass 0. It doesn't really matter because this is the only item in our queue, okay? Now, as long as the queue is not empty, we're going to repeat our algorithm. So, while the queue is not empty, in every iteration, we want to remove one item from the queue, and that is the node we're going to visit. So queue.remove. This will return a node entry object, but we want to get the node. So we access the node field and store the result over here. Next, we should add this node to the list of visited nodes. So visited.add current. Pretty straightforward. So here we are doing a breadth first traversal. We got a node from the queue. Now we should look at all its unvisited neighbors, exactly like what we had in the breadth first traversal algorithm. So here we need a for loop to look at all the neighbors of this node. For var, edge, and current.get edges. Now, if we have visited the target of this edge, we should move on to the next iteration. So if visited contains edge.to, that is the neighboring node, then we're going to continue. Otherwise, we should calculate a new distance. That is super easy. We set new distance. Now we need to go to our distances table and get the distance to the current node. So distances.get current. Once we have that, then we add the weight of the edge to the result. So edge.weight. So let's say currently we are in the middle of our graph, and it takes 5 miles to get to the current node from the starting node. Now, to calculate the distance to the current neighbor, we should know the distance from the starting point to the current point plus the weight of this edge, okay? So now we have a new distance. We should compare this with what we have currently recorded in our distances table. So if the new distance is smaller than what we have currently recorded, that is distances.get edge.to. So edge.to is our neighbor. If the new distance that we have is smaller than what we have, then we should update our table. So we call distances.replace. What we have for edge.to, or the neighboring node, we want to replace this with the new distance. Now that we have a new distance, we should push this neighbor to our queue. So queue.add, we give it a new node entry and pass edge.to, as well as the new distance as the priority. So if the new distance is shorter, this entry is going to be moved to the beginning of our priority queue. Okay? Then in the next iteration, we'll remove one more item from the queue and repeat all these steps as long as the queue is not empty. When our queue becomes empty, our distances table is ready, so we can return the shortest distance to the target node. Distances.get nodes.get to. As simple as that. We have done most of the work, so finding the shortest path is going to be super easy. First, I'm going to rename this method to get shortest path. Always pay great attention to the name of your methods and their return type. So here we're asking for the shortest path, but we're returning an integer. This is a common problem that I see in a lot of people's code, even developers with years of experience. It's like asking for a book, but getting an airplane. Don't write code like this. So what should we return here? We want to return a path object. This path should specify a series of steps, okay? So let's add a new class here, path. We give it a list of strings, list of string. In this program, we're storing string objects in our graph, but in a real application, we want to store person objects or cities or airports. So if we store person objects in our graph, the path class should store a list of persons, not node objects, because node is an implementation detail of our graph class. We don't want to expose it outside of the graph, okay? So let's import the list class. We call this field nodes and set it to a new array list. Now, because this is private, we cannot access it from the outside. So here we need a public method for adding a new node. So string node. And here we call nodes.add node. Simple as that. If this concept is foreign to you, you need to watch the second part of my Ultimate Java series. This is all about object-oriented programming. All right, back to our graph class. So here we want to return a path object. That is better. Now, in this method, we should create a hash table for storing the previous nodes. So we need a map of node to node. We call it previous nodes and set it to a new hash map. Now here, we're not going to initialize this like how we did with the distances table. Instead, when we discover a new distance or a shorter path, we're going to update our previous nodes table. So previous nodes dot put, the target is edge.to, that is our neighbor, and the previous node is where we are right now, the current node, okay? Now, once we're done here, at the end, we can build the shortest path using a stack. So let's say we want to find the shortest path between A and E. We know that we arrived at E via B, and we arrived at B via A. So here we can add all these previous nodes to a stack and then pop the stack, and then these nodes are going to come out in the right order. But initially we want to add the target node because this is not in the previous nodes column. Okay? So after our while loop, let's create a stack. We're going to use the implementation in the java.util package. So in this stack, we're going to have a bunch of nodes. Initially, we want to add the ending node to the stack. So stack.push nodes.get to. Now we want to find all the previous nodes. So we declare a variable like previous. And here we go to our previous nodes hash table and get the previous of this target node. Now I don't want to repeat this expression over here. So let's extract this and store it in a separate variable on the top. Later, we're going to add validation. So that would be another use case for this refactoring. ToNode equals nodes.get to. Now, let's fix this error. So we pass ToNode and ToNode. All right. Now, while this previous is not null, we're going to push this previous node onto our stack. So stack.push previous, and then set previous to the previous of the current node. So we go to our hash table one more time and get the previous node of this node. Our stack is ready. Now we can create a path object from this stack. So let's create a path object. While the stack is not empty, we're going to call path.add. Here we pop the stack. This will return a node object, but we need a string. So we access the label field. And finally, we'll return the path object. Now our code is getting too lengthy, so I would prefer to extract all this logic into a separate private method. Let's call that private path build path. Here we need the target node, to node. Now we can move all this logic over here. Cut, and then paste it here. We also need the previous nodes, so let's add that as a parameter. Map of node to node called previous nodes. So this method needs two parameters, a hash table and a target node. Now back to our find shortest path method. Here we can call this method, give it the previous nodes and the target node. That is better. Now we have one compilation error here. Let's see what is that. I forgot to return the path for our new method. Now let's test this implementation. So here in the main class, I've created a very simple graph. We only have 3 nodes. We have an edge from A to B with the weight of 1, one from B to C with the weight of 2, and a direct edge from A to C with the weight of 10. Obviously, the shortest path from A to C is via B, even though we have a direct path from A to C. But let's verify this. So let's call graph that gets shortest path from A to C, store the result over here, and then print it on the console. So this is the default representation of an object as a string. To fix this, we have to overwrite the toString method in the path class. So over here, that is super easy. We have done this several times before. We generate a toString method. And here, we simply call nodes.toString. Now let's test this one more time. There you go. So here's the shortest path from A to C. Now, what if we pass an invalid node here, like K? We get a null pointer exception. So we need to go back to our graph class and perform validation. After we get the from node, we want to make sure it's not null. If it's null, we're going to throw a new illegal argument exception. Similarly, for the to node, we're going to check to see if it's null. If it is, we're going to throw a new illegal argument exception. So this is the complete implementation of Dijkstra's shortest path algorithm. In the last section, we talked about finding cycles in a directed graph. Now, the algorithm we talked about there doesn't work for an undirected graph. Let me explain why. So here we have a simple undirected graph without a cycle. Now, if we run our previous algorithm, we'll put A and B in the visiting set, but because there is an edge from B to A, and A is still in the visiting set, our algorithm would think there is a cycle in this graph. So it detects a cycle between every 2 nodes connected by an edge. So here we need a different algorithm. We're still going to use a depth-first search, but as we're navigating in our graph, we should pass the parent of each node to its neighbors to prevent going back to that parent. So let's add another edge here and form a cycle. We start our depth-first search from any node. Let's say A. We put A in the set of visited nodes. Now we should explore the neighbors of A. We can go to B or C. The order doesn't matter. Let's go to B. Now, B has 2 neighbors, A and C. We don't want to go back to where we came from, right? So as we move from A to B, we should pass A as the previous or the parent node. Now, when exploring the neighbors of B, we know that we came from A, so we're not going to go in that direction. Instead, we go to C. Similarly, we pass B down, so we don't go back to it from C. Now, C has one other neighbor, but we have already visited A. So we have a cycle in this graph. Now, in this example, we started from A and all these nodes are connected. But what if we had a complex graph and some nodes were not reachable from A? That's very easy to solve. We need to start our search from every unvisited node in this graph. So we need a for loop. We iterate over all the nodes of this graph. If a node is not visited, we start a depth-first search on that node. So now I want you to implement this algorithm in code. Add a method called hasCycle to our weighted graph class. It shouldn't take you more than 15 to 20 minutes. So I will see you soon. So here in the weighted graph class, let's add a new public method, public boolean hasCycle. Here we need to iterate over all the nodes in this graph. and start a depth-first search from that node. So for each node, in nodes.values, now here we need a recursive method for our depth-first search. So private boolean has cycle. We need a node here. We also need the parent of that node, as well as the set of visited nodes. Let me put it on your line. So set of node called visited. Now let's focus on the private method first. So in this method, first we need to add this node to the visited set. Then we need to look at all the neighbors of this node. So for each edge, in node.getEdges, now if this neighbor is where we came from, we're going to ignore that. We're going to get another neighbor. So if edge.to equals the parent, that means this is where we came from. We're going to continue and look at another neighbor. Otherwise, if this neighbor we're going to visit exists in the visited set, that means we have a cycle, so we should return true. So if visited contains edge.to, then we're going to return true immediately. There is no need to look at the other neighbors. Otherwise, if we haven't visited this neighbor, now we should recursively visit that neighbor. So we call the hasCycle method, give it this neighbor. Now as the parent, we're going to pass the current node. That is the node that we have over here. So we pass these two node objects, as well as the set of visited nodes. Now this will return a Boolean value. If we find a cycle, we'll return true immediately. There is no need to look at the other neighbors. Now we can improve this code, as I showed you in the last section. We don't really need this local variable. We can put this expression in our if statement. That is better. We can also combine these two if statements. So if we have previously visited this node, or there is a cycle in this node, then we're going to return true. Okay. Otherwise, we'll look at another neighbor. Once we have visited all the neighbors, that means we didn't find a cycle, so we should return false from this method. So here's our private recursive method. Now back to our public method. Here we need to create a set of nodes. So a set of node, we call it visited, and set it to a new hash set. Now for each node in this graph, if you haven't seen this node before, so if visited doesn't contain this node, then we're going to start our depth-first search from this node. So we call our private recursive method, pass this node as the first argument. Now here we don't have a parent because we're starting our search right here. So we pass null. And then we pass our set of visited nodes. Now this will return a Boolean value. If it's true, we're going to return true immediately. We don't need to look at the other nodes in this graph. Otherwise, if we have visited all the nodes and we couldn't find a cycle, we're going to return false. Now here we have too much nesting. We can improve this code by combining these two if statements. So if we haven't visited this node before and this node has a cycle, then we're going to return true. Like this. That is better. Now let's test our implementation. So back in the main class, here we have 3 nodes and 2 edges, one from A to B and one from B to C. Obviously, there is no cycle, but let's verify that. So print graph has cycle. We get false, beautiful. What if we add an edge from C to A? Now we have a cycle. So this is how we detect a cycle in undirected graphs. Another topic that comes up in coding interviews is the minimum spanning tree of a graph. So let's say the nodes of this graph represent our offices and their edges represent connection between these offices. Now let's imagine connecting these offices requires laying physical cables between them. The more cables we need, the more we have to pay. Now, how can we minimize our cost while keeping all these offices connected? It doesn't matter if they're directly or indirectly connected. Well, we can remove the edge between A and C. That's unnecessary because A is still connected to C via B, right? We can also remove the edge between B and D. What we're left with is called a spanning tree. So we have converted a graph to a tree. As I told you before, a tree is a graph without a cycle. Now, spanning trees are not unique. There are many ways to create a spanning tree for a given graph. So back to our original graph, we can also remove the edges between A and B and C. All our nodes are still connected, so this is another spanning tree. Basically, if we have n nodes in a graph, our spanning trees should have exactly n-1 edges. So here we have 4 nodes and 3 edges. The moment we add another edge, we form a cycle in this graph, and that graph is no longer a tree. If we have fewer than n-1 edges, not all of our nodes are connected. So a spanning tree should have exactly n-1 edges, okay? Now each spanning tree has a cost, and that is the sum of the weight of its edges. So the cost of this tree is 12. What about the other spanning tree? The cost of this tree is 8. So this one is cheaper, and it's a better solution for reducing the cost of our cables. Now, there are algorithms for finding the minimum spanning tree of a graph. This is the tree with the minimum cost. In the next video, we're going to look at one of those popular algorithms called Prim's algorithm. In this video, we're going to look at Prim's algorithm, which is one of the popular algorithms for finding the minimum spanning tree of a graph. We'll start off by selecting a node. It can be any node in this graph. So let's pick A. We look at the edges of this node and pick the one with the minimum weight. A has 2 edges. The edge with the minimum weight is the one from A to C. So we add this edge and its target node to our tree and then go to C. Now our tree has 2 nodes, A and C. We should extend this tree and add another node. But which node? Well, we have to look at all the edges connected to the existing nodes and then pick the one with the minimum weight. These are the edges from A to B, from C to B, and from C to D. We're not considering the edge from B to D because it's not connected to the nodes of our tree. So at each step, we want to maintain a tree. We want to make sure all nodes are connected. So out of all these edges available, the smallest is the one from C to B. So we add this edge and its target node to our tree. Again, we have to look at the edges connected to all the nodes of our tree. We have 3 edges to pick from. The smallest is the one from B to A, but we have already visited A, so we're not interested in this. The next smallest edge is the one from B to D. We have not visited D yet, so let's add this edge and its target node to our tree. Now we have visited all the nodes, and we have a minimum spanning tree. So the idea of Prim's algorithm is to extend the tree by adding the smallest connected edge. This is another example of a greedy algorithm. I've highlighted the word connected here because at each step we want to maintain a tree. So we're not interested in edges that are not connected to the nodes currently in the tree, okay? Now let's talk about implementation. At each step, we want to pick the edge with the minimum weight out of the edges connected to the existing nodes. How are we going to do that? Well, every time we visit a node, we add the edges to unvisited neighbors to a list or pool of available edges. These are the edges that are connected to our tree, right? Now, in this list, we want to pick the edge with the minimum weight. What's the ideal data structure for that? A priority queue. With a priority queue, we can pick the minimum weight edge in constant time. We're going to repeat this until we have added all the nodes of our graph to our spanning tree. Now, how are we going to represent this spanning tree? We can use our weighted graph class. So we don't need to create a new class called spanning tree because a tree is essentially a graph. Our spanning tree is going to have all the nodes of our graph, but with fewer edges, right? So we'll spend 20 minutes on this and then come back see my solution. Let's start by adding a new method. Public, we're going to return a weighted graph, and we call our method getMinimum spanning tree. Always use descriptive names for your methods. Now here we need to create a weighted graph object. So weighted graph, we call it tree or minimum spanning tree. I'm going to go with the name tree because it's shorter, and it's obvious that here we're creating a minimum spanning tree. So there is no need to come up with a long variable name like minimum spanning tree. It's way too long. So let's just call this tree. We set it to a new weighted graph. We can simplify this code. We have repeated weighted graph twice, so we can replace this with var. That's better. Now we need a priority queue. So priority queue. We're going to use the one in the java.util package, not the one we created earlier. So let's use this. And in this queue, we're going to have a bunch of edges because we want to find the minimum weight edge, right? So let's call this edges and set it to a new priority queue. Now, earlier I told you that here we need to pass a comparator object in the constructor. So the priority queue can figure out how to order these edges. We're going to order them based on their weight. So edges with a smaller weight should appear at the front of the queue. So here we're going to use the comparator interface. We call this factory method comparing int. This will return a comparator object for comparing two integers. Now in this method, we should pass a function using a shorthand syntax. So this function should take an edge and return the weight of that edge. This comparator object then will compare the edge objects based on their weight. Okay. Again, if this is confusing, don't worry. I'm going to cover this in detail in my upcoming Advanced Java course. So here we have our priority queue. Now we need to pick a node from our graph and add all of its edges to this priority queue. That's our starting point. So let's pick a node. We go to the nodes hash table. We get the values. Now here we can convert this to an array and pick the first item, but I showed you a better way. So here we call the iterator method. This will return an iterator object. We can use that to read one item from this collection. So we call the next method, and this will return a node object. Let's call that start node. Now we need to add the edges of this node to our priority queue. So edges, then add all. We can add a bunch of edges together. Here we call start node and then call the get edges method. This is better than doing a for each loop and adding one edge at a time. It's just cleaner. Now we should also add this start node to our spanning tree. So every time we discover a node, we add it to our tree. Okay. So here we call tree.add node. We should pass a string here. So start node.label. Now what is interesting here is that these nodes are completely different. We are not working with the same node object in memory. So start node is the node in our graph. We pass the label of this node to our tree, and our tree will internally create another node with the same label and store it in memory. So all the nodes and edges in our tree are going to be different from the nodes and edges in our graph. Okay. Now we're done with the initialization. Now we should repeat. So as long as our tree doesn't have all the nodes in our graph, we should repeat. So here we need a while loop. While tree.nodes.size is less than the nodes that we have in this graph, we're going to repeat. In every iteration, we're going to remove the minimum edge weight from our queue. So edges.remove, this will return the minimum edge. Now we should check to see if we have visited the target of this edge. If we have visited that node, we should get another edge from our queue. Okay. So if tree.nodes.contains key minimum edge .2, that is our target node. Now here we should pass a string. Because this contains key method is part of our hash table, it takes a string and tells us if we have an entry with this key in our hash table. So if this condition is true, then we're going to continue. Now, I don't quite like this code. It's a little bit too lengthy. I would prefer to create a new method in our graph called contains node. Just like we have add node, we're going to have contains node. So this is the end of our method. Now, here in the weighted graph class, let's add a new method. Public boolean contains node, takes a string. And here we return nodes that contains key label. With this method, we can replace this code with something shorter and more expressive. So if this tree contains this node, then we're going to continue. By the way, I made this public because it's a useful method to have in a graph. So from the outside, we can call graph. Here we have add node, we have contains node. Potentially in the future, we can have remove node and so on. Okay. Now, back to our while loop. If we have visited the target node, then we're going to continue. Otherwise, we should add this node to our tree. So tree, then add node, min edge, the label. Now, I don't like that we have repeated this expression twice. I would prefer to extract this in a local variable. Let's call it next node and set it to min edge, 2. Okay. Now we can make this code even better. So we replace this with next node. And one more time here. So we're adding the next node to our tree. We should also add this edge to our tree. So tree, then add edge. Here we pass min edge, that from the label. Next, we should pass the label of the next node. And finally, the weight of this edge. Now let me put this on a new line. That's better. So we add this edge and the target node to our tree. Next, we need to add all the edges connected to this next node to our priority queue. So in the next iteration, we can look at all the connected edges and pick the one with the minimum weight. So here we do a for each loop. For each edge, a next node that get edges. Now, if our tree doesn't contain the target node, then we're going to add the edge to our priority queue. In other words, if you have visited the target node, we're not interested in this edge. So if our tree doesn't contain this node, that is edge to the label, then we're going to add this edge to our priority queue. So edges that add edge. Okay. So let's quickly recap. As long as our tree doesn't contain all the nodes of our graph, in every iteration, we're going to pick the edge with the minimum weight from our queue. Then we check to see if this edge is connected to a node that currently exists in our tree. If that's true, then we're going to pick another edge. Okay. Otherwise, we're going to add this edge and the target node to our tree. And then we're going to add all the edges connected to the target node to our priority queue. But we're only interested in the edges that connect us to a node that we haven't visited so far. Okay. Now, after this while loop, our tree is complete, so we can return it over here. Now let's test our implementation. So here in the main class, I've created the graph that we had in the previous video. Now let's call graph that get minimum spanning tree. We store the result over here, and then we can print it. Now, if you compare the result with the minimum spanning tree that we came up with in the last video, you can see they're identical. Now, what if our graph doesn't have any edges? We got an exception, no such element exception. So let's see what's going on here. So in our while loop, when we're trying to get the minimum edge, we get this exception. So to handle this, before this while loop, we need an if statement. If our queue is empty, we're simply going to return our empty tree. Let's run the program one more time. Beautiful. What if our graph doesn't have any nodes? Let's see if our code works. As I told you before, we should always test these edge cases. Now, there are times that I probably forgot to do that in the videos, but you got the point. So here we have another exception, no such element exception. We got that exception on this line when we're trying to add the first node to our tree. So right at the beginning, before we even create this priority queue, we check to see if we don't have any nodes in this graph. So if the nodes hash table is empty, we're going to return this blank tree. Let's try it one more time. There you go. So this is the proper way to implement the prims algorithm. Now, if you look at the other implementations online, you can see their code is disgusting, literally disgusting. Honestly, when I was reviewing this algorithm and its implementation, because I studied this long time ago, almost 20 years ago back at school. So I had to review it and look at various implementations to refresh my memory. I looked at these implementations and honestly, I just wanted to throw up looking at the code written by these so-called computer scientists. Your code should always be clean and expressive, so others can read it like a story. This is what differentiates you from the average programmer out there. Throughout the course, I've tried to show you numerous ways to refactor your code and make it cleaner and more expressive, and I hope you have learned a lot. So that brings us to the end of this course. I want to congratulate you for all your effort and finishing the course, and I hope to see you again in my other courses. If you enjoyed this course, please tell others about it. I really appreciate your support. With your support, I can create more courses like this for you and other people around the world. So thank you and have a fantastic day.